Imagine a city, a vast and complex metropolis, skyscrapers, neighborhoods, 100 kilometers of roads connecting everything. Now, shrink that entire city down until it fits on your fingertip. That's essentially what a computer chip is. What you're looking at when you see a chip, magnified hundreds of times, is a computing city. It has distinct districts for different functions: memory, storage, processing power. It is the silent, powerful engine inside your phone, inside your car, inside your gaming console, and across the modern world we interact with every single day. The scale is almost impossible to truly grasp. These tiny cities are populated by billions of microscopic electronic devices. The most fundamental of these is the transistor. Think of a transistor as a simple light switch. It can be either on or off, allowing or blocking current. A single chip today can hold over 50 billion of these switches. Combine billions of them, and you get the logic that powers everything. Sending a text message, rendering a complex 3D world in a video game. It's the foundation of digital information, a binary choice repeated billions of times. Globally, we produce more than 1 trillion of these chips every year. That's roughly 20 trillion transistors every single second. It's a production volume that challenges the imagination, a constant global hum of creation. And what's even more incredible, this is done in fewer than 500 specialized factories worldwide. These factories, fabrication plants or fabs, are among the most advanced and cleanest places on Earth, where this tiny construction happens. So how do we build so many tiny, intricately connected devices so fast? There is no microscopic construction crew stacking parts one by one. The secret is photolithography. This process is like building every single house, road, skyscraper in our tiny city at once. It uses light as a measuring tool and as a sculpting tool, etching complex patterns onto a silicon canvas with unbelievable precision, layer after painstaking layer. The entire process begins with a perfect round and ultra-pure slice of silicon, known as a wafer. This wafer, usually about the size of a dinner plate, is the foundation for hundreds of chips. Before anything can be built, this foundation must be flawlessly clean. It is doused in a series of powerful solvents and acids to strip away any and every impurity, down to the last stray atom. Then, the wafer is placed inside an extremely hot furnace, where oxygen gas reacts with the silicon to grow a perfect thin layer of silicon dioxide, which acts as an insulator. Once the insulating layer is ready, it's time to add a light-sensitive material. A liquid called photoresist is dripped onto the center of the wafer. The wafer is then spun at incredibly high speeds, causing the liquid to spread out into a perfectly uniform, razor-thin coating. After it's spun on, the wafer is gently baked to harden this photoresist layer, preparing it for the most critical step. This layer is what will hold the blueprint for the city's next level of construction, reacting precisely to the light that is about to be shined on it. Next, we bring in the blueprint and the light. A specialized stencil, called a mask, is positioned just above the wafer. This mask contains the intricate pattern for one layer of the chip's circuitry. Powerful ultraviolet light is then shown through the mask. In the areas where the light passes through and hits the wafer, a chemical reaction occurs within the photoresist, weakening its chemical bonds. The wafer is then washed in another chemical solution that dissolves and washes away only the weakened photoresist, leaving behind a perfect stencil of the mask's pattern on the wafer's surface. With the pattern now defined, it's time to make it permanent. An etching machine uses reactive gases to remove the exposed silicon dioxide, creating tiny windows that drill the mask's pattern down to the raw silicon surface below. An ion implanter then shoots a high-energy beam of atoms, like boron or phosphorus, into these patterned openings. These implanted atoms change the electrical properties of the silicon, creating the essential positive and negative regions that form the foundation of the transistor switch. This entire cycle of layering, patterning, and etching is repeated hundreds of times to build the chip. Building these microscopic cities is an incredibly resource-intensive process. Fabs run 24 hours a day, 7 days a week. It takes about 3 months to guide a single wafer through the process. Hundreds of steps turn pure silicon into hundreds of finished chips. This non-stop operation consumes enormous amounts of electricity. The high-temperature furnaces never cool down. The vacuum pumps run constantly. Massive air handlers filter the air, thousands of times cleaner than an operating room. The process also requires a staggering volume of water. Wafers are cleaned repeatedly between steps. This uses ultra-pure water, far cleaner than anything you could drink. Chemical mechanical polishing, or CMP, grinds chip layers perfectly flat. CMP uses a continuous flow of water to flush away debris. Cleaning and polishing can create nearly 30 gallons of liquid waste per wafer. This wastewater is full of chemicals and microscopic particles that must be treated. Then there are the chemicals and gases, solvents, acids, bases, specialized process gases, vast amounts of nitrogen, vast amounts of helium. Other gases used in etching and deposition are potent greenhouse contributors. Fabs use scrubbers to minimize impact. Scrubbers decompose harmful gases and dissolve them into treatable wastewater. But this crucial step requires even more electricity and even more water. As demand for smaller, more powerful chips grows, new environmental challenges arise. Making ever-shrinking features requires photoresists based on PFAS chemicals. PFAS are often called forever chemicals because they don't break down easily. Waste from these materials is ending up in our ecosystems and even our bodies, with potential long-term health risks. The march of progress has a hidden and growing environmental bill attached to it. There is no question that computer chips are modern marvels. They have completely transformed our world, connecting us in ways we never thought possible, unlocking incredible creative and scientific potential. The factories that build them are themselves engineering wonders, pushing the boundaries of what is physically possible. But as our appetite for more powerful devices accelerates, the fabrication process is starting to hit hard sustainability limits. In some regions, governments are already beginning to ration water to farmers in favor of keeping the local chip fabs running. This is not a sustainable path forward. The future of computing and the health of our environment depends on us finding a better way. We need to develop the next generation of fabs, factories that are leaner, cleaner, and greener. This means fundamentally rethinking the tools and processes that have served us for decades. The goal must be to reduce the immense consumption of electricity, water, to minimize the use of harsh chemicals, and to eliminate the generation of hazardous waste wherever possible, creating a circular economy within the fab itself. The good news is that the immense brainpower of the semiconductor industry is beginning to focus on these challenges. Researchers are exploring new materials that could replace PFAS-based photoresists with safer, biodegradable alternatives. Engineers are designing smarter tools that use less energy and recycle process gases more efficiently. There is a growing push to develop advanced water treatment systems that can clean and reuse the vast quantities of water consumed by a fab, significantly reducing its pull from local sources and creating a closed-loop system. The challenge is great, but the path forward is a hopeful one. The same ingenuity that allowed us to build cities on a speck of dust can be harnessed to build them more responsibly.